so let's start with some very easy problem. F x y is equal to, so these are, I think this is from the book, minus 4xy plus 1. Okay, so the problem is always this one. I have a function. You see that it is defined everywhere. It's a polynomial. And find the nature of all the critical points. So the first thing is this bottleneck to find the critical points. So this is contrary to what I told you because it's not a quadratic polynomial. But the polynomial is simple. It will be very easy to find the critical points. Okay? Otherwise, we are in trouble. So we start with the derivative of this. Fx equals 4x cubed minus 4y equals 0. Fy equals 4y cubed minus 4x equals 0. So from here we see that y is equal to x cubed. And from here we see that x is equal to y cubed. So putting this in here now, we see that y is equal to x to the 9, right? Y equals y to the 9. Okay. Okay, so now I can solve this. So remember that this means that this is y, taking y to the other side, y8 minus 1 equals 0. So this tells me that y equals 0 or y equals 1 or y equals minus 1. Okay, and then we have this. From here it follows that then x equals 0 here, y equals 1 here, or y equals minus 1 here. So these are the critical points. Okay, so this implies this, this implies this, this implies this. So conclusion, so we managed to get over this critical part, this bottleneck, very easily because the polynomial is cooked up. So the idea for simple polynomials is to show how this is implemented. Okay, so the critical points are 0, 0, 1, 1, and minus 1, minus 1. Now, after you find such things, you should always take 5 or 10 seconds to check if it makes sense. The function is symmetric in x and y, so it's expected that the critical points are symmetric. This is not scientific, okay? So this is just gut feeling, okay? If I have such a symmetric polynomial and I find that one of the critical points is 7 minus 13, then I would go back and check. Okay? There's no reason for that, but you should feel that you don't expect something like that in a symmetric polynomial. Okay, so then we calculate. Next, we want to apply the second derivative test, and second derivative test tells me to calculate the discriminant. For the discriminant, I need these second derivatives. Okay, so next we calculate fxx. So the derivative of this with respect to x is 12x squared. This is 0. The derivative of this with respect to y is 12y squared. Now fxy, since this is a polynomial, it's a second partial, third partial, all partials are continuous. So mixed partials are of the same. I can calculate any of them. fxy, let's say. So the derivative of this with respect to y is minus 4. Check that without anybody seeing you. The derivative of this with respect to x is also the same. If they are different, then you made a mistake. So you are pointing at something. Did I make a mistake? No? Okay, good. Okay, so now you calculate the discriminant. Discriminant, you remind yourself, is this expression. Okay, so it is this times this, 144 x squared y squared minus square of this is 16. Okay, so we calculate, now we calculate the discriminant at 0, 0. Okay, at 0, 0, the discriminant is minus 16, but in most cases here, the discriminant is some complicated expression, but in your mind, you start putting values here and you realize that it's going to be negative. So you don't need the exact value. Check the second derivative test, okay? We never care what the value of this is, except that it is positive or negative. So here we check that immediately. It is minus 16, but I don't care. It's negative. So I immediately apply this. This is a saddle point. 0, 0 is a saddle point. Okay, I calculate the discriminant here. So 1, 1, these are 1. This is 144 minus 16 is positive. No need to stretch your brain to find the exact value. This is positive. So 1, 1 is a local minimum. And discriminant minus 1, I noticed that I'm taking squares here, so it will be the same. So this is positive. Minus 1 is a local minimum. Okay, so I'm almost done. This 2 prime I didn't need because discriminant is not 0. And now I have to check what happens to this function as x and y are going to infinity. Here you look at the largest powers generally, okay? Because if this thing is going to be infinite, x and y must go to infinite, at least one of them. So it is always the leading part here. This is the part where the power is 4. This is the part where the power is 2. This is the part the power is 0. So you always take the leading part. That is the dominating thing. This tells if the function goes to plus or minus infinity, okay? To convince yourself, suppose that x and y are huge numbers, each with 10 million digits. Okay? So these numbers exist. So you are taking a 10 million digit number and taking its fourth power, and here you are looking at second powers. So this is just a detail. You start writing the fourth powers, sum of the fourth powers of 10 million digit numbers, and way later you start writing the contributions of these things. Okay? So these are just little guys. Nobody listens to them. Whether this function will go to infinity or not will always be determined by this. Okay, so now it's easy. These are even powers. It's positive. So this will never go to minus infinity, but it will go to plus infinity. Okay, so that's the observation we write. Okay, so let's do that here. So limit of f x y is infinite as x and y go to plus or minus infinite because of the leading power, the leading terms, x to the 4 plus y to the 4, and it never goes to, well, never, it does there only once. Okay, and it doesn't go to minus infinity, so it is bounded below. Okay. Now, if the function is bounded below, if the function has a minimum, the derivative must be, the tangent plane must be horizontal there, and it must be a critical point, so it must be among these. Okay. We have two local minimum points. So one of them is the absolute minimum. But the function is symmetric, so both of them give you the absolute minimum. Okay? So the function has global minimum, and sometimes we call this absolute minimum at 1, 1 and minus 1, minus 1. Okay? If the function was not symmetric, you should calculate the value here and the value here. One of them is smaller, and it would be the absolute minimum. But you see here, whether you put plus or minus 1, you'll get the same value for the function here. Okay, so this is the end of the solution. So we did the number 4. We analyzed the function. It was easy here. And again, from symmetry, we see that this function has absolute minimum or global minimum, whichever terminology you like, here and here. And this is a saddle point, and it's unbounded from above. Okay, so now we totally understand this function. You plot this on Wolfram, and you see that this algebraic calculation, this conclusion which we did without looking at any pictures is correct. Okay, so that's the power of doing calculations. Okay, so that's one thing. Now, of course, the interesting, you see, this is very typical. Once you pass this point, you apply the second derivative test, you have this, and here you have to examine what the function is doing. It may be tricky because this leading term may not be easy, but again, that's why I told you to look at the number theory books. You see this part, if it is quadratic, then you can check it. If it is not quadratic, it's tricky. But again, you have to, if it shows up in an exam or as an exercise in the book, it must be something that you can do easily. In real life, okay, so you work on it, you ask your friends, you come to the math department, we'll help you. Okay, so in real life it's different. But I'm saying these things to point out that there's a problem here. Okay, so in real life, this part is not easy. You have to check if the function goes to infinity or not. Sometimes it's easy to check that it goes to infinity, sometimes not. Okay. After that, then again, the rest is routine. If you know the function is bounded from below, one of the local minimums is going to be absolute minimum. If the function is bounded from above, one of the local maximums will be absolute maximum. You write those things, and that's the end of the problem. Now, the trick is, other than this and this, the trick is when, the tricky part I'll say, is when the discriminant is 0. Okay? We have absolutely no rules for that. So I'll give you two examples. One of them is from Okan Hoca. So this is a very nice problem. So the lesson of this exercise is to show you that there is no prescribed method for this. You are on your own. You just play with the function and try to see if it's a minimum, maximum, or a saddle point. Okay, so the second problem is this one, which I'm taking from Okan Hoca. So this is x cubed minus 2x squared plus xy squared. Okay, so first of all, for this part is suddenly easy. The function is unbounded both from above and below because, again, the leading term is x cubed. It tells us what's happening. The others are small here. Okay, so you can take, for example, y equals 0. Okay, so this is the function. When x has millions and millions of digits, nobody asks his opinion. So the function is determined like this. This goes both to plus infinity and minus infinity. So the function is unbounded. Okay, so we will not have global mean or global max. Okay, so let's make a note of this. Okay, so the function is unbounded, so has no global mean or max. Okay, so limit of f x 0, so along the x-axis as x goes to plus or minus infinity is plus or minus infinity. Okay, so that's why it's unbounded. Okay, so we are relieved of this. Now let's look at the second, the critical points. Fx is equal to 3x squared minus 4x plus y squared equals 0. Fy is equal to 2xy equals 0. Okay, so this is the bottleneck, but you see now it is cooked up so that it is easy to solve. I start from here. Either x equals 0 or y equals 0. So either x equals 0 or y equals 0. So what happens when x is equal to 0? Now I look at this one. Okay, this x0, y squared is equal to 0. So fx equals 0 gives y equals 0. Okay, so 0, 0 is a critical point. So 0, 0 is a critical point. Okay, so now what happens if y equals 0? If y equals 0, well, I obtained it from this equation, so I put it into this equation. I check what happens. This is 0. When that is 0, you see I have here 3x squared minus 4x equals 0. Okay, so here this is x times 3x minus 4 equals 0. Okay, so to make this thing, well, okay, here either x equals 0, this is done. Okay, I already have it here, or x equals 4 over 3. Okay, to make life easier, you say we prefer to do in mathematics department as follows: either x equals 0 or x different than 0. Saying that x different than 0 gives you extra information. So here I don't have this case anymore. Okay, so it makes life a little bit easier. But this is not difficult either, because here sometimes you recover the same critical point you recovered here. Just a note. So 4 over 3, 0 is another critical point. Okay. So then we apply the second derivative test. I look at fxx is 6x minus 4. Fyy is equal to 2x. And fxy is equal to 2y. I also check secretly that the derivative of this with respect to x is also the same. Okay. So discriminant is equal to 6x minus 4 times 2x minus 4y squared. Okay, so let's erase this now. Okay, so we immediately see that 0, 0 will give discriminant 0. So let's delay that case. Let's check what happens at this critical point. At the critical point 4 over 3, 0, I get, so I calculated that here, 4 over 3. This is 32 over 3, so 32 over 3. So as far as we are interested, it is positive. Okay. Then I look at the sign of one of these things. Both of them should have the same sign, since the discriminant is positive. So you check one of them. The other one is easier, so let's check the other one. Fy at 4 over 3. Niye öyle oldu ya? Ha, tamam. 4 over 3, 0. This is equal to 2x. So this is what? 8 over 3 positive. Okay. So this is a 4 over 3, 0 is a local minimum. Okay. Discriminant 0, 0 is 0. So the second derivative test fails. The second derivative test fails. We examine the behavior of f around the origin. Well, the origin, because the origin is a critical point. So now this is what we do. So you see, from what we do from here on is typical of this function and this point. Okay, so for other functions this will not work. So here we notice that, or Okan Hoca has noticed that f of x, y is equal to x times x minus 1 square plus y square minus 1. Okay, just simplify this, you obtain that expression. So this also reveals you how such examples are cooked up. You start from here. Okay. Now this is, you see, this is, I call this g of x. Okay. G of x equals 0 is a circle of radius 1. This is the radius, center 1, 0, 1, 0, passing through the origin. Okay, you put x equals 0, y equals 0, g is 0. And inside the circle, G is negative, right? Inside this circle, Gx is negative. Outside, it is positive. Okay, there is no doubt about this, because outside you can make x and y very, very large, and obviously it will be positive because you are adding positive things. You are only trying to beat -1 here, this poor guy, by choosing x and y very large outside the circle. It will be positive. So inside, g of x is positive. Inside the circle, x is also positive. Let me draw a picture. Okay, so this is x and y coordinates. So this to see what's so I'll draw. So this is the circle. Okay, with center here. Inside here you see x is positive and x is positive. Okay, so f is positive. F is negative because I'm multiplying negative by positive. F is negative inside the circle. Okay, so let me use red to denote the signs of f. So here f is negative, here f is negative. Outside here, g is positive, x is positive here. So it is function is positive here, positive here. But actually this is enough. But let's also check what happens here. Here, this is outside the circle, so g is positive, x is negative. Okay, so this is negative here, and it's negative here. Okay, so maybe I make the pluses green because that's the picture that we want. Okay, so it's plus here, plus here. And at the origin, notice that f of 0 is 0. Note f of 0, 0 is 0. Okay, there. Okay, here the function is positive, but here, I was going to use green. So here you see it is positive, it is positive. So if you approach the origin along this region, this is a local minimum. It is 0 here, positive here. If you approach the origin in some other direction, you see, I am only interested in what happens around the origin. Here, the function is negative. It becomes 0 here, then it is again negative. So it's a local maximum when you follow this region. So this function is this point is a saddle point. Okay, so here you have to write, see the figure for the signs of f. Okay, so around the conclusion is around 0, 0. There are points. There are always points less than 0 and larger than 0. So 0, 0. Well, this part I'm comparing with this number. If you are approaching the origin along a path in the green region, the value of the function along that path is, you see, always larger than the value of the function at 0. So this number here is 0, 0. This number here is 0, 0. Okay? So this is a saddle point. Okay? So, any questions? Well, don't ask me how did you find this, because you see this cooked up like this. But in real life, you'll start playing with this thing. Okay. So normally, what would I do? I will just plot this, look at this shape. The shape will suggest me something, and then I'll try to prove this. That's always what you do in mathematics. First, you get a feeling. You make a claim. You don't mind whether your claim will turn out to be wrong, because in your real life, you make millions of guesses and almost all of them turn out to be wrong. So there is no embarrassment there. But if you don't have a claim to prove, then you are lost. Okay, so you say, I think this is a local minimum for this function. You try to prove that it's a local minimum. Then you notice that there are always points where the function takes positive values. Then you say, okay, I'll change my claim. I'll try to prove that it's a saddle point. Okay? Then you try to prove that it's a saddle point. When you're focused on this, then you ignore the other parts. And if your guess is correct, you reach your guess. If your guess is wrong, along the way, you find out why it's wrong. Okay? So that's a strategy to solve problems. Let me do one more example before we...
If we couldn't find a way like this, would it be logical to try to use a more higher derivative test in an exam?
Well, forget about the exam, but I don't know if there are any higher derivative tests. If you invent one, then you'll be famous. Okay.
Can't we take the derivative of the expression that we used to prove?
Which expression? F? Well, we already took two derivatives of this.
If we get further in the Taylor expression?
Yeah, but you see, the reason why second derivative test fails was while the second derivative test worked is all the terms before that, the first derivatives were 0. Okay, but now the second derivative, the terms of the second derivative terms of the Taylor series is not 0. The discriminant is 0. So when you take the third derivatives also, you have this third derivative plus the second derivative. You couldn't handle this one, now you are putting this one. Maybe, depending on the function, it may tell you something, but I don't expect that. But you are right, you'll try anything, okay? If the discriminant is 0, and if your life depends on finding out what the nature of this critical point is, then you'll try anything. And one of them will work, okay? So there's no such thing as unsolvable with these problems. So one of them will work for that problem, okay? So don't lose hope. I'll do one more exercise where the discriminant is 0 before we start our quiz. So this first example was very recent. The next example I'll give you is the first example I learned when I was a calculus student. So this is something about milattan önce. Okay. So what was this? This was the second problem, right? So the third problem. So I learned this problem in 1973. So this is the function f x y equals x cubed plus x y squared plus y squared minus 3x. Okay. So this is from 1973. I learned this from my calculus teacher. So he was teaching us calculus. He said he'll give f to half of the class, and he did. Okay, so first of all, we see that the function is unbounded. Okay, you put y equals 0. This is a cubic in x, so it is unbounded. So notice f is unbounded. Just check f x 0. Okay, so this goes to plus or minus infinity as x goes to plus or minus infinity. So there is no global mean or max. There are local stuff. Okay, we take the derivatives. Fx equals 3x squared plus y squared minus 3. I want to solve this. Fy equals 2xy plus 2y equals 0. So since we are going to have a quiz, let me just write the solutions. So from here, we get 1, 0, and minus 1, 0 are the only critical points. Okay, so you see, it's easier to start from here because here you know that either y is equal to 0 or x plus 1 is equal to 0. So you continue from there. Then we look at, now we apply the second derivative test. So I'll just write these things quickly. Fxy, 2y, fy, yeah, 2yy is equal to 2x plus 1. Let's write these things. And therefore, discriminant is equal to 12x x plus 1 minus 4y square. Discriminant at 1, 0 is equal to, well, it's positive. Then we look at fxx 1, 0. Well, it's 6 positive. Okay, so 1, 0 is a local minimum. Okay, and of course, discriminant at minus 1, 0 is 0. So the second derivative test fails. The second derivative test fails. Now we have to be creative. We have to use our creativity. Okay. So for this thing, okay, let me erase something here. This turns out to be a saddle point. So I have to find two directions, two paths. You have to find two paths passing through these critical points. Along one path, this point has to be a maximum. Along the other path, it has to be a minimum. Okay, so then it means it's a saddle point. So this is how you, the first path is very easy. If you look at this thing, you restrict the function to the x-axis. Okay, so you will see that at that point, the function has what, minimum or maximum. Okay. So we suspect that minus 1, 0 is a saddle point. Okay. We look for two paths passing through minus 1, 0 along such that along one path minus 1, 0 gives local min. Along the other it gives local max. Okay, so one path, the first path is x-axis. Okay, so then f of x0 becomes what? x cubed minus 3x. Okay, so this is one-dimensional thing. So since I want to give time for the quiz, check that. So check that. Minus 1. So x equals minus 1, of course. X equals minus 1 is local maximum here. Okay, so you take the derivative, equated to 0. It's also 0 at some other point, but at minus 1 it is 0. Then you look at the second derivative. It tells you the second derivative is negative at that point, so it tells you that the shape of the curve around that point is concave down, so the function is a maximum there. Okay, so that's just what we did last semester. The second part is where your creativity shines. The second path is x equals, let me see, y cubed over 3 minus 1. Okay, so here f of y cubed minus 3 minus 1. So x is this, y is y. The function, after you do this, the function becomes y to the power 6 over 27 plus 2. Okay, so now you don't even have to take derivatives. By staring at it, you see that y equals 0. Okay, so in our case, y equals 0 will give you minus 1, 0. Y equals 0 is a local minimum for this, because any y non-zero will give you a positive value here. It will add up to 2, but y equals 0 will be the minimum value. Okay, so here y equals 0 is minimum, well, it gives the minimum point. Okay, So this corresponds to -1, 0 here, okay, is local minimum point. Okay, so we found two paths along which, along one of them, the point behaves as local maximum. Along the other, it behaves as local minimum. So the conclusion, this is a saddle point. So -1, 0 is really, we say really because we suspect it here. Now it's really a saddle point. Okay, so this is what happens. So I have some other problems, but you see the nature of the problems is this. The only way for you to learn this is to solve lots of problems, because you see the theory is simple. Once you develop the theory, it is simple. The rest is you have to get your hand used to it. Okay, now let's have a quiz. The quiz is about writing the equation of a tangent line to a surface, but of course there is a twist there.